All right, let us consider now a spherical surface. A spherical surface interface boundary considering images formed by refraction. So I'm going to take some surface boundary. It's like this. We'll go ahead and draw in a principal axis sort of thing going on. And I'm going to go ahead and take a point object on this principal axis. We're going to have, this is some material now here that just keeps on going. We'll say that it has an index of refraction N2, and we're initially in a material with an index of refraction N1. So we're going to consider where the image is being produced regarding the system and our refraction taking place. So let us consider some light rays that emit off of this. One is just a light ray that just keeps on going, goes like this, and then continues to go nice and straight along the principal axis. And then we can take another one, say, well, we've got another light ray that may go like this, strikes the principal axis here, and what do we know? There's a normal to that location. That normal is aligned with the center of curvature, because again, this is a spherical surface here. And we'll say that we are going from a lower index to a higher index in this case. So we'll just go ahead and let N1 be less than N2 so that we note that this ray will bend inward towards the normal. And I'm going to draw it in like this. There goes some change in direction. Goes, and then we got ourselves some intersection. Intersection. That's where the image is going to be produced. So let's start naming some angles here and some representations of things. So let's go ahead and draw in a couple of things here. I'm going to call this angle here alpha. I'm going to call this angle here beta. I'm going to call this angle here gamma. I'm going to call this angle here theta 1. I'm going to call this angle here theta 2. And should we name one more angle? Why not? I'll call this angle, this angle here, I'll call it phi. We've got a bunch of angles named within this. We also want to name out some distances as well. So I'm going to translate this downward and say that that has some height. Distance above the principal axis in which the light ray that we're considering is striking. We'll get into some little discrepancies here momentarily. I'm going to call this distance here P, the object distance. I'm going to call this distance here, that should be lined up with this. Call this distance here R. And I'm going to call this distance here Q. We've got object distance, radius of curvature, and image distance, P, Q, and R. Now notice something. I'm measuring everything relative to the translation point of the light ray that intersects at the boundary here, not from the actual surface here. So if there's this little bit of space right here, and we are ultimately ignoring that little bit. This portion. You say, how can you ignore that portion? It has some amount that you're neglecting. That seems pretty bad. And while that is true, we want to be living under the paraxial limitation here. So really, in order to draw this out, we have to have pretty large angles. But this derivation that we're going to do here is assuming that we have small angles. And we'll just put, ignoring this point, since we are assuming small angles, living within the paraxial limitation. So if you considered an actual really small angle, something maybe striking right here as opposed to being there, that distance, the shift, lateral shift, is very, very negligible. Here it doesn't look like it because that's just, we had to draw them as big angles, but we're going to actually say that they're small angles so that we can do some nice math, figure out some correlations here. So ultimately we want to be able to get some sort of expression that correlates P, Q, and R, and the difference of the indices of refraction as well, N1 and N2. So let's just go ahead and start to develop some relationships within this. Number one, we have N1 times the sine of theta 1 is equal to N2 times the sine of a theta 2. That's just our good old Snell's law there. And we're going to use the paraxial limitation, which says that for small angles, sine of theta is approximately theta. Which then allows us to go ahead and write that N1 times theta 1 is equal to N2 times theta 2 under this approximation. So that's going to be one important one right there. We can start looking at the composition of some other things here. Let's make some triangles. Let us go ahead and say that this angle alpha plus this angle beta plus this angle phi have to be equal to, you guessed it, 180 degrees. So we've got alpha plus beta plus phi must be equal to 180 degrees. Well, what is phi? Can we write this angle phi in terms of some other things? And the answer to that is, I sure hope so. And hope indeed we can, because those three have to be 180. We've got that this total angle right here has to be equal to 180 degrees, which is phi plus theta 1. So we have phi plus theta 1 is equal to 180 degrees, which then gives us that phi is equal to 180 minus theta 1. And thus we can write this expression in terms of what we have. So alpha plus beta plus 180 degrees minus theta 1 is equal to 180 degrees, which then says alpha plus beta is equal to theta 1. So I'm going to box that up a little bit. That's a nice little relation. Theta 1's equivalent to alpha plus beta. Let us get another relationship. How about we use something with this gamma down there? And yeah, let's just go ahead and do it. We could look at gamma, theta 2, and then this angle right there. Let's name that something else. This is just going to be equal to, well, that's 180 minus beta. So we have to have that gamma plus 180 minus beta plus theta 2 all adds up to be 180 degrees. So we've got ourselves gamma plus 180 degrees minus beta plus theta 2 is equal to 180 degrees, which leaves us with gamma minus beta. Let's write this the other way. Move the gamma over there and the beta over there, and write that theta 2 is equal to beta minus gamma. So we've got ourselves a few nice relations there between some of these angles. Utilize all the angles there, and then indices of refraction. Let's look at some more regarding this. Some triangles now. Gotta love triangles here. We've got this triangle right here. Nice right triangle. that we can take on out and draw this to see some things like this. We've got this angle alpha, we've got the base P, and then we've got H there. What can we say about that? We could say that the tangent of alpha is H over P. Great. Well, let's look for another triangle here. Take another one and say, well, what about this triangle here? Have another nice right triangle involving H, beta. Draw that one out as well. Have ourselves something like this. Got beta, H, now that is R. We can write another expression similar to this, where we've got the tangent of beta is H over R. Let's see if there's one more triangle that we could use, and there is indeed. Oops, using red, sorry about that. Come all the way down here, all the way over here. We got this big long triangle here that has a gamma, an H, and a Q. So ourselves gamma, H, Q, and we could write that the tangent of gamma is equal to H over Q. So, what can we do with all of this? Well, for small angles, there's another approximation that says the tangent of theta is approximately theta. Again, in radians. That's the same small angle approximation that applies with the sine of theta, which is the tangent of theta 2. So these three relations here can be even simplified more to say that alpha is H over P, beta is H over R, and gamma is H over Q. So now what do we want to do? We want to go back to these three relations and embed these new ones within that. So we know that N1 times theta 1 is equal to N2 times theta 2. And we know that theta 1 is equal to this, and theta 2 is equal to this. What if we go ahead and multiply both sides of this by N1, and both sides of this by N2? Then we'll have an N1 theta 1 and an N2 theta 2 that have to be equal to one another. That sounds pretty fantastic. So, let us say then that N1 multiplied by gamma plus beta is equal to N1 theta 1, and N2 multiplied by beta minus gamma is equal to N2 theta 2. And from our previous relation up there, we had that N1 theta 1 is equal to N2 theta 2. So, we must have then that N1 times alpha plus beta is equal to N2 times beta minus gamma. Well, what do we have in terms of alpha, beta, and gamma? We have those relate back to H, which is a common factor in all of them, P, Q, and R. Let's put those in there. We can now write N1 multiplied by H over P plus N1 multiplied by H over R is equal to N2 times H over R minus N2 times H over Q. Factor of H, factor of H, factor of H, factor of H, common factor, gone. Which then allows us to write. Used all this stuff here, so I'm gonna go ahead and erase it. Further write this as N1 divided by P plus N1 divided by R is equal to N2 divided by R minus N2 divided by Q. I'm going to take this term, throw it on this side. I'm going to take this term, throw it on the other side. And we can write this then as n1 over p plus n2 over q is equal to n2 minus n1 over r. If we know the indices of refraction, we know the radius of curvature of the surface boundary, and we know where we put the object relative to that surface boundary, we know where the image is being produced. This is very similar to the expression that we utilize for spherical mirrors. A little bit different because we have indices of refraction, yet it's very, very much the same. Of course, again, this assumes paraxial limitation is not being exceeded, but serves as a very decent approximation for most cases in which we have large radii of curvature and small lateral or vertical distances being considered. Well, this was from going from a smaller index of refraction to a larger index of refraction. What happens if we want to go the other way? Reproduce all this stuff, do everything over again, and come to the same exact expression. But we need a sign convention. That was the same thing that we ended up with mirrors. So, this works for n1 less than n2 and n1 greater than n2 when using proper sign conventions. That ultimately comes down to P, Q, and R. Single interactions only is all that we'll be looking at. P's positive on the front side. And we define the front side ultimately by the side that the object is on. Front side, back side. Light wants to go from the front side to the back side when we're looking at images formed by a refraction. Unlike reflection where light is constrained to the front side. And this makes a little bit different sign interpretation. But this is what we've got. We've got that Q is positive if the image is on the back side and negative if the image is on the front side. Really, this comes back down to real images versus virtual images and the sign plus for real, minus for virtual. The only locations that we can have real images being produced are on the backside because, well, that's where light physically exists after the interaction. If we are going to get the intersection on the backside, that's going to be a real image, which we consider then to have a positive value. If instead we end up getting an image on the front side, light doesn't physically exist on the front side after the interaction regarding the refracted light. So you'd be having to trace stuff back, which gives us a virtual image and that correlating with a negative Q. And then we've got the radius of curvature. R is positive on the backside. Excuse me. R is positive when C is on the backside. Say when the center of curvature is on the backside. And negative when C is on the front. And